Yes. So good evening, everyone. Welcome to this session. We have planned for a little bit of probability and then also this open channel flow, channel hydraulics. So there are some questions which I need to take up from the forum. So you had said that this you didn't understand some part of it. So let me go back to that solution. Yeah, I hope the screen is visible. Or maybe I can redo this because anyway, so let me redo this. You have a polynomial of the form so you have a polynomial as 1 plus x plus it is 1 plus 2x plus 3x square and so on up to 2026 x power 2025. And we have certain statements. It has a global minimum, maximum, global minimum. It does not have a global minimum, and it is not continuous. So last time I said it is easier to rule out what are all the wrong options. So let us look at the last option first, because that is easy to look at. So you know that polynomials are infinitely differentiable. Where? On the real line, right? So is there a value of x for which the derivative does not exist? So if you have a sharp point, say for example, you have a curve like this, at this point the derivative does not exist because the value of the derivative to the left of it and the right of it are different. Or if you have a point where the function is becoming unbounded, it is taking infinite value. At that point, it is not continuous. Or if its derivative is taking such values, it is not differentiable at that point. But this is a polynomial. It has only positive powers of x. See, it has only positive powers of x. And for all, when you have positive powers of x, for any finite value of x, this is a real number. It is a real number and it is continuous. It is differentiable everywhere. So this is, if it is differentiable, it is obviously continuous. You don't have any break. So so option D is obviously wrong. So D is wrong because polynomials are infinitely differentiable. You can So if you differentiate this expression 2026 number of times, you will get a 0. And you can also keep differentiating it further. So up to 2026 derivatives exist, and beyond that it is 0 identically. Therefore, it is differentiable, therefore it is continuous. So option D is wrong. Then the other statements are about the existence of global minimum and global maximum. So if the question is about local minimum and local maximum, we need to look at the derivatives. But since it is about global minimum and maximum, let us look at how the function varies with x. So we are looking for global minimum or maximum. So when do we say a value is a global maximum for a function? So if f of x is less than or equal to some m for all x belonging to some interval, say a to b, then m is a global maximum of the function f of x in the interval a to b. Right? It is simple. It is just when you say so it should be less than or equal to, that is, if f of x is less than or equal to a given m, and it should be and f of x naught should be equal to m for some x naught in a to b. That is, you take an interval, take some interval a to b, and you see a certain function which is taking a maximum value here, and within this interval a to b, everywhere else the function is small. So you call it a global maximum of this function in this interval. Now, in our question, they have not specified any interval, so it means the interval is basically the entire real line from minus infinity to infinity. So if a global maximum should exist, you can see that the function clearly has to be bounded. That so the first condition is boundedness. If you can find so you find a value which is not exceeded by the function, that is a bound for the function. And if that bound is reached at any point, that is the maximum value of the function. Therefore, if a maximum global maximum has to exist, then it has to be bounded first of all. So therefore, let us look at if the function is bounded or not. So to see if the function is bounded or not, we examine the polynomial. We see all the coefficients are positive. All the coefficients are positive. What does this mean if all the coefficients are positive? If you take f dash of x, you get say 2 plus 6x plus 12x square plus 2026 into 2025 x power 2024. Now, when you say x greater than 0, you see that this is positive, all these are positive, and all the coefficients are positive, which means when x is greater than 0, f dash of x is greater than 0 always. And when so this is one point. So which means the slope is always in the positive. It is strictly greater than 0. Therefore, when x is greater than 0, the function is increasing. So the slope is strictly greater than 0. Therefore, the function is increasing, which means as x tends to plus infinity, f of x tends to plus infinity. Therefore, there is no global maximum. No global maximum. The maximum value that is attained by the function is infinity. Infinity is not typically treated as a global maximum because it is an undefined mathematical object, right? So as x tends to infinity, the function grows unboundedly. Therefore, there is no global maximum, which means our option, which option it is? Option B is also wrong. So we said option B is also wrong. Now either A or C has to be right because one says it has a global minimum and the other says it doesn't have. Again, let us look at it. So if you look at again, so when x is less than 0, you look at the derivatives. So in x is less than 0 and for sufficiently large x, for sufficiently large x, say x is greater than or less than or equal to -2, right? So when x is less than -2, what will happen? Look at f dash of x. So f dash of x is 2. So f dash of x is 2 plus you have 6x plus 12x square plus something up to 2026 into 2025 x power 2024. Now this is a positive coefficient, no problem. But look at this. This is 6 into -2 or bigger values. This is 12 into -2 the whole square. Right, this is 12 into -2 the whole square. That is fine. This is the positive value. Then subsequent values will take this alternating plus and minus signs. But if you look at sufficiently, so if you let me go to the next page. So you have f of x as 1 plus 2x plus 3x square up to 2026 x power 2025. And f dash of x is 2 plus 6x plus 12x square and so on up to 2026, 2025 x power 2024. Now, if we look at negative x, when x is less than 0, what happens? Leave the derivative for now. Right now, it's not useful. When x is less than 0, f of x is, so let us say x is equal to some minus y, where y is greater than 0, right? Then f of x is nothing but 1 minus 2y plus 3y square plus 2026 y power 2025. Sorry, you can't take this out. So this will be alternating. So you have, let us write f of x is 1 minus 2y minus, so we'll have negative terms and also positive terms. So the second one will give, so this, if you differentiate, you get, so sorry, you don't differentiate, this is 2y. So here you'll have 3y square, and here you will have 4y cube, and here we'll have 5y power 4, and so on. And here this also goes on. Now look at this expression. So with successive values, when you take, so x is negative and x we have taken as this positive value. So as y tends to a large negative value, say a large positive value, say y tends to some infinity, you have this term which is unbounded and this is negative. So this term approaches negative infinity and this term approaches infinity. So basically, and if you look at its derivative, it also follows the same thing. So basically, if you take successive terms, as you take very large negative values of x, depending on where you stop, if you take an so this is up to 2000. This is even, right? So up to 2026 y power 2025. Whereas here you will have 2025 y power 2024. Now, when you take a very large value of y, this term will dominate. What does this mean? When y is very large, this entire expression is approaching minus infinity. This will be smaller. So for a very large y power 2025 is much greater than y power 2024 for whatever values you have. So this term begins to dominate. Therefore, it will go faster to minus infinity than plus infinity. Therefore, as y tends to infinity, that is, as x tends to minus infinity, f of x tends to minus infinity as well. Therefore, there is no local global minimum. Right. So if you sketch the graph of the function, when x is less than 0 and it's very large, it approaches from minus infinity. But there are certain oscillations because when x is less than 0, the sign of f dash of x is not, it is not either it's not positive or negative, it switches. So there are some oscillations, and when x is greater than 0, it increases monotonically. So this is how, so there is, in general, there is no upper bound or a lower bound. Therefore, the global maximum is infinity and the global minimum is also infinity. Therefore, a global maximum or minimum does not exist. So the correct option is option C. So if you still, so if you're still doubtful about this, maybe you can see the plot, right? Is that okay? Is your doubt clear?
Yes, sir, it's clear.
Yeah. So sometimes this is a good imagining the plot of the functions always helps. So if whenever you have such questions regarding boundedness, increasing, decreasing, or in these cases, it's always helpful to have some visual view of, say, exponential function, trigonometric function. When you have product of two functions, in those cases, it always helps to have a plot in your mind, think in terms of the plot. So just to check your check our solution, let me show. So if say x, you take it from -10 to 10. And y, let me construct it by the given polynomial. So we are summing them up to 2020, 25, 26. So and the sum is, it is n(x power n-1). So it is ii star dot star x power ii-1. Now let us plot x comma y. Yeah, so you can see that okay, why is it minus? Started from -10, right? Yeah, so you can see the maximum value is going to some nonsensical 10 power 299. So that is like that is almost infinity. So let me minimize the range. So it's the same. So if you zoom in close to this, you see in between. So for let me limit. So this is how the function behaves. When x is less than 0, it drops very fast. It drops very fast to a negative value, which is unbounded. So it keeps going. And when x is greater than 0, it rises indefinitely to a very large positive value. Therefore, there is neither a global maximum nor a global minimum. So that is just to demonstrate. Now let us get into today's session. So you had asked for and the other question. Yes, coming to the other question. So this looks like all 4 options are wrong, but the answers I get are 300 and 350. So to solve this problem, let me. So it is given we have a cost function. So the selling price is wrong. So the selling price is fixed at rupees 300 per unit, and the cost price is it is given as 230 plus rupees 230 plus 0.1 p plus 9,000 by p per unit. And totally P units are produced. So companies manufacturing products at P units per day. So the selling price and cost price is given. What is the production level minimizing the cost per unit? So if it has to minimize the cost per unit, then we have, say, minimize cost per unit. What is cost per unit? It is this. So we have to minimize C of P, cost per unit, which is given as this, which means you just set C dash of P equal to 0. This is just usual calculus. So the first term vanishes. The first term is a constant, so you get 0 plus 0.1, and this is 1 by P, so it is minus 1 by P square. So it's minus 9000 by P square is equal to 0, which means P square is equal to 9000 divided by 0.1. So you get P is square root of 90,000, which is 300 units per day. And then what the second part of the question is total profit per day. So what is the total profit? Total profit is S into, so S is per unit, and we have P units per day. So S into, so profit, let us call it R. So it is P, S into P minus C into P. So what is SP? SP is 300P minus 230P plus 0.1P plus 9000 by P again into P. So 0.1 P square and this into P. So 300 minus 230 is 70P minus 0.1 P square minus 9000, assuming P not equal to 0. Right? P is equal to 0, you can't do the cancellation. But if P is not equal to 0, this is the profit per day. Now minimize the profit. That is what they want. So this is a function of P. So set dr by dP equal to 0. So what does that mean? It is 70P minus 0.2P, and this vanishes. It's a constant, is equal to 0, which means P is equal to sorry, 70, not P. 70 minus 0.2 P is equal to 0. So P is 70 by 0.2, which is about 350 units per day. So the correct option in their format is something like 300 and 350, but we don't have it in the options. Probably something is wrong in the options, but I feel this is there is no confusion here. Given based on the given data, this is the only way this problem can be solved. So did you attempt and did you get the same answers?
So I did not understand how to proceed with this.
Oh, okay. So this is how we do it. So they have given the selling price of the product per unit, which is right, which is what the product, 1 unit of the product is sold at. Cost of the product is the cost involved in manufacturing 1 unit of the product, that is this. So total profit in a day. So first part is easy. The first part they are telling just to where it is. Yeah, the production level minimizing the cost per unit is what? So what is cost per unit? This is the cost per unit, and they want to minimize this. So always that, if you want to minimize or maximize a function, set its derivative equal to 0. That is fine. And then if you want to so this is a okay, there is something we need to check. So this is basically a problem in optimization. You either here you want to minimize the cost per unit and you want to minimize the total profit in a day. So this is the cost per unit, set its derivative equal to 0. So this is how we solve for it. And the solution I get is 300 units per day, minimizes the cost. We can also find what is the cost, right? So let us find what is C of. So what is C of 300 units per day? So C of 300 units per day is 230 plus 0.1 into 300. plus 9,000 divided by 300. So, oh, okay. So the minimum cost is rupees 290 per unit. And the maximum, that is fine. So how do we know it is a minimum? Then check, if you really want to know if it is a minimum or a maximum, check for something slightly nearby 300. So, right, you can go and check the second derivative. So if you look at the second derivative will be plus 2 into 9,000 by p cube. So if c dash of p equal to 0 and c double dash of p is greater than 0, so it is a minimum. And if c double dash of p is less than 0, it is a maximum. Right. So if the slope is going from positive to negative, then slope is decreasing. Therefore, c dash double dash of p is less than 0 when it's a maximum, and c double dash of p is greater than 0 when it is a minimum. Now the second part of question is talking about the total profit. So if p units are sold in an entire day, we have the selling price of 1 unit, cost price of 1 unit. So total profit will be S into P minus C into P. So this is the function that we want to minimize. Again, to minimize, what do we do? Set its derivative equal to 0. So then what happens? You set this, you do this. So that becomes 70 minus 0.2P equal to 0. So let me check. So this is 70p minus 0.1p square minus 9,000. Yeah. So its derivative is this. Now p turns out to be 350 units per day. If you take p as 350, then r is minimized. Now let us find what is r of 350. So it is 70 into 350 minus 0.1 into 350 square minus 9,000. So this turns out to be, let me check. So 70p minus 0.1p square plus 0 equal to 0. So p is 70 by 0.2, which is 350. P by, yeah. So 70, so it is 70 into 350 minus 0.1 into 350 square minus 9,000. So this is about the total profit is 3250 per day. Now, if you see again, if you check the second derivative here, so the first derivative is 70 minus 0.2p, and the second derivative is minus 0.2. So it's actually a maximum. Yeah, but they want a minimum. So, but this is a quadratic function. So fine. So there's no this cannot have a minimum. The minimum is when p equal to 0, we get minus 9,000, but that is not the correct thing. So if you check for 349 or somewhere in between, it's 70 into 349 minus 0.1 into 349 square minus 9,000. So if you take a point 349, this expression turns out to be something like 3249. And if you take 351, minus 9,000. It's again 3249. So this has a maximum. This has maximum at p equal to 350 units. Right. So if at p is equal to 350, you have 3250. And if you take a small value of p less than 350, say 349 or 348, then it is less than 3250. And for a value of P greater than 350, you have a value again which is less than 3250. Therefore, P equal to 350 corresponds to a global and a local maximum. And similarly, for 300, here you can check it for the cost price at something less than 300 and greater than 300. So that turns out to be, so you have 230 plus 0.1 into cost price of 290, 300 plus 9,000 divided by 301 squared. So it is 230 plus 0.1 into 301 plus 9,000 divided by 301 squared. So for the value of 301, you get something like 260, which is less and at a value of say 299. You again get some value higher. So therefore, this is a minimum and this is a maximum. But we don't have, so 300 and 350 are fine. That is the correct value of the production level, minimizing the cost per unit and total profit per day are 290 and 3250. Sorry, those are the values, but the production level is 300 and 350. So there is some problem with the options, but this is how you do it. Is that okay? Do you get it?
So we are taking R as profit, right?
Yeah, R is profit.
So
Yeah, you can tell if there's
if profit, so for they are asking cost should be minimum.
Yes,
So in
yes.
that case, cost should be minimum. Okay. So you are maximizing the profit so that the cost should be minimum. Okay.
No. That is not what I'm doing. So their question is in two parts. So we have two answers for this. So the first part is the production level minimizing the cost per unit is the first part of the answer. And the second part of the question is whatever they say minimizing, but there is no minimum for that function. It's a maximum. So there is some issue with the question. So the second part, if they mean what maximizes the total profit per day, that is the second part. So yeah, so there is no simultaneous. So there is no one value of P which minimizes the cost per unit and maximizes the profit per day simultaneously. These are two different parts in the question. So you have two different answers. Right? Is that okay? So, and their options are all incorrect. So, the question asks the production level, which is actually the number of units per day, but this 290 is actually it is the profit. Sorry, it is the minimum cost of production, minimum cost per unit. So, there are issues with that question. So the question is in two parts basically. You need to find out the whatever minimizes the cost price per unit and uh, and whatever maximizes the profit. So if that is the case, you can also find out the profit at 300 maybe. So this is the profit, total profit, 300p minus this thing. So if you compute it at 300, it is 70 into 300 minus 0.1 into 300 square minus 9,000. So Okay, so R of 300 is rupees 3,000 per day. So the maximum, the profit corresponding to P equal to 300 is rupees 3,000 per day, but that is not the maximum profit. The maximum profit is rupees 3,250 per day, which we obtained by del R by del P equal to 0. And the minimum cost prices we are obtaining by del C by del P equal to 0. So yeah, so basically the question is not clear. So there is this is the variable. This is the only variable they have. The unknown variable is P. They are producing at that rate, and the cost depends in this manner. Selling price is fixed, so it is 300 P. Cost price is this C multiplied by P. The production level minimizing the cost per unit is the production level P, and that we found it is 300, right? We said del C by del P equal to 0, and we got P is equal to square root of 90,000, which is 300 per day. At that level, the total profit is 3,000, but that is not what we are asked. If we are asked the maximum profit per day, it is, again, you said del R by del P equal to 0, and you get the production level which maximizes the profit is rupees. It is 350 per day. So yeah, the question and its options are not consistent. So if at all, if you say option A is kind of close because it minimizes the cost price, and 290 is rupees 290 and 3,000 is rupees 3,000. This is the profit per day, and this is the cost per unit when P is equal to 300. So yes, is that okay? Did it make sense or?
I need to rethink about this question, but it's okay. We can move further.
Yeah. Yeah, the question is little not, it is not phrased properly. The issue is you have two objectives. One is with one variable, you can't optimize two things. So so C will become minimum at some P and R will become maximum at some other P. There is no single P that maximizes that meets both the conditions, right? So, but mathematically, I hope you get it. Whenever you want to minimize or maximize a function, this is what you do. And so that this is what you do. Okay, so let us proceed. So okay, so the next 10 minutes or so we'll look at we'll revise probability as she had requested in the last session. Where random variables. We start with random variables, moments of a random variable, and then solving problems. Maybe we'll take it up later because we have to look at this channel hydraulics as well. So right. So let us start with random variables. So if you remember what we had covered, we have a random experiment. So random experiment is something for which there is an uncertainty associated with the result. You have something called the sample space. Let us denote it by omega. And in the sample space, you have many points or elements of this set, which are called the outcomes. Let's call the outcomes as some small omega. What happened? Yeah, let us call this outcomes as small omega. And we define something as event, which is a subset of omega. And corresponding to every event, we assign a number, which is called the probability. And that probability has to satisfy certain conditions. One is it lies between 0 and 1. And then it is the probability of sample space is equal to 1. And for disjoint events, we have probability of E1 plus probability of E2 is equal to probability of E1 union E2. So these were the three basic conditions that the probability had to satisfy. So probability we defined as a function from the power set of the sample space to the interval 0 to 1, the real interval 0 to 1. So this was the basic thing. Now, why did we introduce random variables? So here probability itself is a function from events, the set of all possible events to this number 0 to 1. But we need something called a random variable. So a random variable is an intermediate function. So random variable x is an intermediate function. Okay, it's not a definition. It's something that I call it's an intermediate function. So a random variable is a function defined on. So x is a function which is defined on the sample space to the real line. So what you do, so probability takes every subset of the sample space and gives a number, but that is not always easy, right? That is in general not an easy task. Suppose you have a say for example you're standing here and you're randomly throwing stones. So the distance at which the stone lands, say let us call it as x, that distance varies continuously, and the set of all possible such distances is uncountably infinite. Therefore, while dealing with such sets, which are uncountably infinite, it does not make sense. It is not easy to go and select some of the elements, some events, and assign a probability manually. In those cases, the probability is rather given by certain continuous functions, right? Continuous functions. So it makes more sense to talk about P of X landing in some A to B. So when we define probability as this kind of functions, it makes sense to have a number correlating with every outcome of the sample space. Therefore, the random variable is such a number. You take every outcome in the sample space and assign a real number to it, such that for every such number, suppose x of a given outcome is equal to some real number a, the probability of x equal to a is defined. It can be 0, but it should be defined. So probability of x, so it is so a random variable is such that the probability of x equal to a given x is equal to so if x, so you take an element here and assign a real number, right? You have the sample space omega. You take a number, you take an outcome and assign a real number. So this is the real line from minus infinity to infinity. Have 0 somewhere. This is some number. This number is what? It is x of omega. If this point is omega, this is x of omega. Now, what does the probability do? It takes this x of omega and assigns a value between 0 and 1. So this is the probability. So this has to lie between 0 and 1 only. This is just the real line, and this is the sample space. So this mapping is x, this mapping is p of x. So random variable is a function which takes in an outcome and returns a real number. That real number can lie anywhere. It is just a real number such that the probability of that x equal to x is equal to the probability of getting that outcome, basically the probability of omega, for which x of omega equal to x. So this is how we define random variables. So the random variable x of omega is a function such that probability of x equal to a given number on the real line is equal to the probability of all the events, right? The probability of the event x equal to say omega, where x of omega is equal to x. So a, sorry, a, in this case a. So again, it becomes easier with examples, right? So let us take the coin tossing experiment, which now let us deal with discrete random variables. And in discrete, let us consider the coin tossing experiment. You have a coin, which you toss it, you get either head or tail. And as I said last time, if it is a fair coin, you know the probability of achieving head is half, and probability of tail is half. But instead, you can always define a random variable such that x of head is equal to uh, 0 and x of tail is equal to 1. So I'm taking an outcome and assigning a real number to it. And we know now what is p of x equal to 0? It is half. P of x equal to 1 is another half. What is p of x equal to half? It is 0. P of x equal to 3 or any other number, it is 0. So this is a discrete random variable. You have outcomes. So these are the outcomes. Sorry, this is a sample space. The elements of the sample space are the outcomes. Corresponding to every outcome, I'm assigning a real number. And corresponding to every real number, I'm assigning a probability. Therefore, x, this is a random variable, and x defined such that x of h equal to 0 and x of t equal to 1 is a random variable. Now, there are certain useful random variables for problem solving. The first type is the Bernoulli distribution. Before we get to distributions, let us see what distributions are. Again, this I have covered earlier. So a distribution function, the distribution function is something called f of x, which is nothing but the probability of the random variable taking a value less than or equal to x. That's all. F of x is called the distribution function or the cumulative distribution function. Such that f of x is equal to the probability of the random variable taking a value less than or equal to a given x. So we have already taken the sample space and mapped it to the real line. Now, assigning probability is just constructing a real valued function. So we have already mapped all the possible outcomes to the real line. The next step is you get a probability number, which is, so this is x, this is omega. And the next step is you just go from here to here. So this is the probability function. But what is the probability function? It takes in a real number and returns a real number. So the probability function is what gives the probability is called a distribution function, which is defined this way. So if you take a value small x on the real line, the probability of x less than or equal to small x is what? It is the probability of occurrence of all events such that the random variable associated with that event takes a value less than or equal to the given x. That's all. So this is the probability in terms of the random variable. This is the probability in terms of the events. Now, I said we look at the Bernoulli distribution. Bernoulli distribution is it deals with experiments with just two outcomes. So tossing a single coin is a Bernoulli distribution. So the two outcomes have either one of them have an outcome p, other has an outcome. One of the outcomes has a probability p, other you can call it has a probability q. But these are the only possible outcomes. It has two mutually exclusive outcomes. Therefore, the other event has the probability 1 minus p. So this is the most basic of all distributions. So it is. So for example, coin tossing is one example. What is more useful than the Bernoulli is the binomial distribution. So you have binomial distribution, which deals with the number of successes in n trials. Now, So how do we, what is it defined as? So suppose you have a coin and toss it n times. What is the probability of getting R number of hits, or let us deal with the random variable X number of hits. Now here the random experiment is not tossing the coin once. You're doing it in n number of trials. Therefore, for this random experiment, you can define the random variable X to be equal to, can define the random variable X to be equal to the number of hits in n trials. So what are all the possible values X can take? You can get one hit. So X can take the value 0, 1, 2, and you can take n also. We can get all hits or we can get all tails. So so a binomial distribution deals with the number of successes in n Bernoulli trials. You assign just one of the outcomes as a success and the other outcome as a failure. So the number of successes in n trials, how do we find that? For this, we use the permutations and combinations idea. N trials correspond to n blanks, and for each blank, you have two outcomes. Right? Now, if you have, suppose, what is the, if X is the number of hits, it means you select X out of these n places. So what is the action of selecting X out of these n places? It is n c X. Once you select them, all of them need to get a success. So let us call P is equal to the probability of success, P of head in a single trial, which is yeah, it can be a biased coin, so it is just P. And 1 minus P is the probability of tail in a given trial. So if this we call it as success, and this we call it as failure, the probability. So once you select X number of blanks out of the n, and in X of these, you need to get success. So what is the probability of success? You get P, and these are independent trials. So again, in n independent Bernoulli trials, the outcome of the first coin is not going to affect the probability of any outcome of the second toss. Therefore, these are independent. What does this mean? If two events are independent, we saw if P of A and B are independent, getting a P of it is equal to P of A times P of B. So getting a success in this trial and getting a success in this trial and getting a success in this trial. So you need to multiply. How many times? There are X such successes. So it is P power X. Not only that, you also need to get failures in n minus X number of trials. So it is into 1 minus P into n minus X. So this is the probability mass function of the binomial distribution. And it's, you know why it is called the binomial distribution, because it has it is of the form of the binomial expansion of a binomial expansion, right? It's just like the binomial expansion. And then so I think we can solve one problem from 2022 gate, or it is quite simple. If you talk, so when you have problems in gate relating to the number of successes in n trials, directly use the binomial distribution, provided each trial has only two outcomes. Therefore, each trial is a Bernoulli outcome. Each trial has only two outcomes. Has two outcomes. And you have all trials are independent. All trials are independent. And you've also seen the other important discrete random variable, which is which we saw in traffic engineering, that is the Poisson distribution. The Poisson distribution deals with the occurrence of rare events. Therefore, suppose you have a large, you have a given time interval. We looked at it. The headways, the time headway, the arrival of vehicles follows a Poisson distribution. So, suppose you have a given time interval and vehicles are equally likely to arrive in any sub interval of the time interval. In that case, they are modeled by a Poisson distribution, where so the number of, if you take the number of arrivals or number of occurrences as x and say the mean arrival rate or mean occurrence rate in the given interval, suppose it is what it is taken as mu. So in this case, what is the random variable? The random variable is the number of occurrences in a given interval. Mu is the mean of the distribution. So it is the mean occurrence rate. Suppose we are standing in a highway and we know that in that highway, the mean arrival rate of vehicles is about 5 vehicles in 1 hour. Then the questions in GATE are typically compute the probability that we see 2 vehicles in 3 hours or something. So always get the mean occurrence rate in that interval. So we have already solved a problem. Say we say mu is say 5 cars per hour for you're standing in a highway, and the highway is very what to say, it's very sparse. You don't have much traffic. So a car is equally likely to arrive at say 1 second or 10 seconds. In that case, it is best modeled by a Poisson distribution. And we know that at an average, 5 cars pass through that point in a given hour. Now the questions are typically like, what is the probability of having, what is the probability of observing 2 cars in say 3 hours? So in that case, the probability of the random variable x is defined as mu power x. Mu is the mean occurrence rate in that interval into e power exponential of minus mu divided by x factorial. So it is 5 cars per hour, but we are looking at 3 hours. Therefore, it is mu is equal to 5 into 3 in this interval. So it is 15. So the probability of observing 2 cars is nothing but, let me plug in my place. So the probability of observing 2 cars is nothing but 15 square by 2 factorial into e power minus 15. So whatever it is, that will be the probability. The other kind of discrete random variable is hypergeometric distribution. So whenever you have the number of trials up to the first success, that is, suppose you do the same coin tossing experiment, you can have either a head or a tail. Suppose the questions are such that what is the probability of observing. So suppose you perform you keep performing trials until you achieve the first head. So you say head is a success. And let us define the random variable x as the number of trials until the first success. Right? You can see the difference. So in the first case, in the binomial distribution, you're looking at the number of successes in a fixed number of trials. In the hypergeometric, this is called the geometric or hypergeometric. In this distribution, you are concerned with the number of trials required until the first success. So what are the possible outcomes? So you keep tossing a coin until you get the first head. So you can get the first head at the first trial itself. You can get one tail, then a head. You can get two tails, then a head. You can get three tails, then a head, and so on. Therefore, what is the so here, what is it? Here, x is equal to the number of trials up to the first success is I can put it as 0 or maybe L1. Here you need 2 trials. Here you need 3 trials and so on. Now, what is the probability of x equal to say probability of the random variable taking a value x? It means you are having how many failures? X minus 1 failures. So 1 minus p raised to the power x minus 1 multiplied by so if you have so the probability of getting so if so when x is equal to 4, you need to get 3 failures and then one success. So it is like 1 minus p power x minus 1 multiplied by p. So this is the case when you have just 2 outcomes. When you have multiple yeah, so this is like with repetition. And all trials are independent. So this is the geometric distribution. You can also have, say, you can also consider the case where you have a bucket with balls colored red and green. You don't know the number of such balls, and you keep drawing a ball until you get the first success. So again, here the case is different because once you take a ball out, if you have totally n number of balls, and say x are of there are m in red color, and red is equal to success. So in this case, once you have taken a ball out, you don't replace it. So without replacement, the probability, the discrete probability mass function is given as, so out of the m, you choose x, and from the remaining, you choose n minus x. So out in n minus x number of trials, you get failure, and in one trial, you get success. So divided by NCX. So this is so yeah, this is the number of so this is the hypergeometric distribution. So basically, the idea of random variables is to translate all the definition of probability from defining it on events to real functions. The other important parts in random variables are mean and variance of distributions. So we have already seen that in the statistics part, we define mean as the average and variance as sigma square. In the case of a distribution, it is slightly different. So if you have a discrete random variable, the mean is defined as summation of xi f of xi, where f is the probability mass function. What is the probability mass function? It is nothing but the probability of the random variable taking a value of x. And the variance is nothing but xi minus mu square, xi minus mu the whole square into f of xi. So this is nothing but the way this divided by summation f of xi will be there. So this is in terms of the relative frequency, something like the relative frequency. But the sum of all probabilities is 1, so you don't need to write down the denominator explicitly. And in the case of a continuous random variable, this just becomes an integral. So again, in the continuous random variable, we have f of x is nothing but the probability of x less than or equal to x, which is called the distribution function. But x doesn't take discrete values. As I said, if you stand here and you just throw stones, it takes a continuous. There are uncountably infinite number of values. So in the continuous case, this is a continuous function. F of x is a continuous function. So you define its derivative as f of x as f dash of x. That's all. And this is called the density function because you are differentiating with respect to x. This is called the probability density function. Therefore, what is the probability of x less than or equal to x? It is nothing but integral from minus infinity to small x f of x dx. So this is the probability. You take the area under the curve from minus infinity to x, you get the probability. You get the first moment of the area under the curve from minus infinity to say infinity. F of x dx. This will give the mu or the expected value, and you take the second moment of the area about the mean of the density function, you get the variance. So mu is also known as the expectation. So this is also called the expectation of the random variable. This is the variance of the random variable. So what do we mean by the expectation? Expectation is you perform the random experiment infinite number of times, and we know each outcome occurs with a certain probability. What is the expected value of the random variable as you perform it infinite number of times? That is the meaning. So uh, again, in continuous, the only random variable that we have for gate is the normal distribution. Where the probability density function is defined as 1 by sigma root 2 pi e power minus x minus mu by sigma the whole square, and you have a half outside. So where sigma is the variance and mu is the mean of the random variable. So basically, this is all we have for gate. And there are things that we deal with two random variables, say x1 and x2. How do we find how those two are related, whether they are independent? There are some concepts related to that. But I have gone through it again. If are there any doubts? You want some part to be repeated again, or is there any? Do you want more problems, or how do I help you? Can you tell?
So I'll try solving some problems. Then if I get stuck, then I'll post it on Google Groups.
Yes. So that will be fine. So is there any? So okay. Then based on our discussion, is it clear what is a random variable, and you have any part that is not clear?
It's clear as of now.
Okay. Okay, fine. So, but again, we are out of time. I cannot do the hydraulics part. Let me do one thing. I'll post these questions right now in the. Let me. Because it's we're behind schedule. Let me explain. Which pages? Pages from 1 to 6. So this is channel hydraulics basics questions. Let me call it set 1. So because we don't have time to discuss this, let me post these questions in the group. You can try it out, and then in the next session we'll solve them. I will also post the material needed for solving the questions, so that because this is the last week I can go for this. Next time I have to look at some other topic. So let me. So this is based on energy depth relationships. These questions are from. So you can try them out. I will also post the material for you to solve them. Right. So because the exam is approaching, let us spend more, because those topics might have been already covered by somebody else. I'll post the relevant. I'll write it down, and I can post whatever the formula and concepts required for solving those questions. You can go through them and right away start solving, because those are relatively easier than other. Those are relatively easier topics. So maybe to make these sessions more effective, let us focus on questions, problem solving alone. Is that okay?
Yes, sir.
So, okay. So you have any other topic that, so last time she wanted probability and we have discussed it at some good length. Do you have any other topics that you find difficulty? We can take it up in the next.
Sir, last class we discussed traffic engineering problems. No, sir, that PDF, can it be uploaded in Google Groups?
Sure. Yes. I think this one, right? This was about random. Yeah. These problems, right?
Yes, sir.
Yeah. Okay. I will upload 3 PDFs. One is for the yeah, I did not upload. Okay, one the traffic engineering concepts, one traffic engineering problems and solutions, and the other with this channel hydraulics problems. Sorry, concepts, so that you can solve the problems. Is that okay?
Okay, sir. Thank you, sir.
Okay, thank you. Stop recording.